a simple experiment.
Definitely Australian.
Rubber tubes, hard thin water, funnel. Okay, we've got some liquid nitrogen in this flask. We'll pour it in carefully. Now, this is an application of Newton's laws.
You should be wearing mitts, asbestos mitts or something, I think.
Okay, so we've just got that there nicely, quietly boiling at 196 degrees. Now, if we put a lid on that didn't have these tubes in, it's extremely
Can't see
dangerous.
little straws coming out of it.
Okay, so that looks in. There we go. One way, one the other way. So right now they're boiling from a liquid to a gas. The nitrogen gas is going out of this safely. One way, one the other way. We're going to rapidly boil this in our cup of water.
Yeah. So phase change, our first week in this class, but now also rotational moment of momentum is what we'll talk about today. Just like the Pelton wheel. So I can't believe that he did what he did. He's touching it, he's pouring it into a funnel. It's above his hand. It's liquid nitrogen, which is what? It's minus 50 Kelvin, something like that. So it's minus 200 centigrade or something. So I think if that goes on your fingers become brittle and they break off. So I don't know. Anyway, so what else? Oh, this is good as well. Anyone speak German here? I don't remember this being in German before, but this is a pump storage scheme, right? This is in the energy transition when you can produce electricity from solar and wind turbines, but can't store it. You need some grid scale storage for it, and one mechanism is pump storage. So when you have excess electricity, more than you can use, you use it to pump water upstream, uphill, to an upper reservoir, as you saw earlier. And then when you need it, when the demand is high, you let it come down. There's losses in the system, so you don't store everything. But if you want that, that's an alternative to have grid scale storage, which you can't really do with battery farms because it's not big enough. So one of the mechanisms for grid scale storage. Other is to convert the electricity into hydrogen and then store the hydrogen underground, and then burn the hydrogen or use it in fuel cells afterwards. So this is the guts of a pump storage scheme. It's a turbine. The water comes down from the right and comes down around this swooshing circular, I guess, angled pipe, and then it goes into the turbine in these, or it might come in on the straight one. Perhaps it comes in the straight one. Goes down through here, through these veins. These veins are slightly angled, so as it comes in vertically, it gets pushed out at 90 degrees. When it gets pushed out at 90 degrees, the blades aren't all radial on that thing. They're slightly offset by an angle, so they spin the wheel. And as a result of spinning the wheel, Abfluss sounds like out. Aufgang is out, right, in German? So Abfluss, outflow? I don't know. So you see it spinning here. So either way, I guess it looks like it comes in on that central thing, spins the turbine, and it gets kicked out to the side. I won't replay it again. And so again, relevant to what we're doing. Pelton wheel, you saw before. Hopefully you can also see that it's really quite similar. We looked at the one from the Kentucky mine for water. This is air. You see the air jet on the right-hand side. And spinning, undershot. So we'll talk about how to do that today. We've kind of already done it. We talked about these veins last time for moving frames of reference. This is kind of cool as well. Not generating power, but just, so a coiled tube. It's got veins on it. You can see the aluminum veins. Someone's just made this thing. See the aluminum veins that get pushed by the river. So it's a water wheel being pushed in this, and it has a collector, which is just about to come out of the water. Collector collects stuff, and so it slowly pushes it along the spiral, and I guess at the end of it you'll see all it's doing is trying to give extra head to the water so that it gets pumped up into a sump, which is off camera. Let's see if we can look to that. So there's a global view of this. Yeah, so it gets pumped up, I don't know, 5 feet. It can't be higher than the height of the top reach of the wheel, which is kind of cool. And what else? So not really so much power conversion, but water tools. And also the essence of what we'll do today is this, kind of a long video, kind of blah, blah. It's a lawn sprinkler that also, in addition to having a sprinkler system on it, which we'll see, has the hose power driving it as a tractor so it moves across your lawn. Which I think it does. So we won't spend all the time going through that, but we'll just look at the business end of it as it gets set up, I think close to the end. Most replayed. Yeah, there you go. So you've seen them all on people's lawns. You know a bit about this, right? So this is angled upwards as you'd want it to be. You know how those arcs are because we did a question with Bernoulli to calculate that. But we haven't done anything to say that if, for instance, these jets were horizontal and oppositely oriented, the velocities that it might go at. But it's very similar to the linear vane. Once the radius gets super long, then the rotation of the thing is very minimal compared to its transit. And so you could think of it just as the static vane that we looked at before. I don't want to play it again. So what else? Is there another one? No, don't want that. But I will go to the other one I had. So this is Pelton wheel. It's in the UK. I guess we can open it up, right? This is in, if I zoom out, you can find out where this is, location-wise. It's in the northern part of the UK. And it's a pump storage scheme. And actually, if you change this to satellite, I think, you can't completely see it. But the idea, this is built probably in the late 1970s, as I recall. My guess is that this is here. So that's where it was. These two lakes are the pump storage lakes. It's a region of Wales that used to be slate mining. It's actually laid to waste because when you mine slate for roofs, the good slates you get might be 10% of the slate and the rest is just junk. And so the slopes are all covered with this man-made scree from slate mining. And one of these lakes would be the upper lake, one of them would be the lower. My guess is that the upper one would be the smaller one, but I don't know that. And then somewhere between these two, underground, there's a big cavern that has a bunch of turbines in it. And those turbines do the things like the Pelton wheel, hence the Pelton wheel being on the surface. I think there are more efficient turbines like the ones that we saw in the German movie there that would be used in this kind of place. And so, I could do under. I don't want to show you my life, but it's always dangerous. I'm trying to think. I don't know. Actually, that's not a much better way to do it. Is this? Wonder. So I'm looking Lanzhou. I bet you this is these are them. Lanzhou is in China. You can see that Lanzhou, and it's the home of this ancient water wheel, which is kind of cool. One of these must be a video from 5 years ago, I think, something like that. This is the Yellow River, actually in full flood spate. This would be in June, I think, and so this is draining the Himalayas and going to the sea in either the East China Sea or the Sea of Japan, depending on which country you live in. And yeah, this is doing exactly the same thing as that small scale thing. So the water wheel is turned, it raises water up in buckets and then dumps them in here at a higher elevation where it can be taken to be used by someone. Maybe that's it. Yeah, so you see it. So same idea. So these blades are in the water, carrying water up to this thing. So I don't know what age that would be, but it's I don't know if it's 2,000 years ago or whatever. So that's it. So that's what we'll talk about today. That's the niceties of what we'll do. I don't know whether I'll do it this way or whether I'll write it out. It's worthwhile maybe going through the stuff on linear momentum. I said that that's the third question in the midterms, which are coming up, not next week, but the week after. And so maybe just go through that. We did it last time, and certainly the things that we talked about last time would be the skills you need to survive. So if you don't have any objections to that, let's spend a couple of minutes playing around with that. I scrolled out the stuff below. I was going to erase it and do it by hand, but let's just use the stuff I have. So you'll remember that the last little while we've talked about conservation of mass, which we're not talking about today, which was W a rho plus rho v dot plus rho dot v equals 0. So that's our easiest equation, because the property in this is a scalar property. W is always the normal to the boundary velocity. So it has no direction. It's really positive or negative, depending on whether it's in or out. And this was conservation of mass. So that was the first one that we dealt with. Perhaps we don't need to go through that again, but you know the sign conventions for this are just like a streamline. And so if this was W1 and W2, this is W. So this is positive, and this is positive, right? This actually is really W dot N. And so the dot product is what gives it the sign convention, which is positive out and negative in, because of the orientations of the normal to the boundary components. And the final one, which we only need when we come to this, is we have W times W dot N. And that comes in this term here, right? This is the dot product that conforms to this. This is the density. This is the area of which it comes. And so we've written this preferentially for conservation of momentum as the sum of the forces, vector, are equal to W plus velocity of the control surface times m dot. This is m dot, mass rate of flow. And m dot is just density, velocity, and the area of which it flows. We note that these are vectors. This is a scalar. This is a vector. Usually we write it for one component, which we've done for the jet lev and the vane and the decapitated cylinder. And so this is also the sum, right, on all the surfaces. And so this would be Wx plus VCSx in the x direction, multiplied by the mass flow rate, equals this. And so the other thing that we also need to know is we need to remember the Fire Department of New York with their hose, which I'm going to draw out to here, which is W plus V control surface. And I mean, these are the concepts. It's much simpler once you get to it, right? And then this is just the velocity from a static observer. So this term here is the velocity that you see if you're looking at it. So this is just V static. Okay, so this is what you see here. This is the Fire Department of New York. This was our vane that we did last time with all those components on it. And this is our easy form of writing it. You don't need to know the integral form of Reynolds transport equation. You just need to know this one, and really you probably only need to know each individual component. So just to summarize the cases that we looked at and how the system simplifies, is that this was our Jetlev guy. Could be girl. Jetpack on. And so it was steady because as much fluid was coming in here as was going out. So by definition, steady state means mass in equals mass out. And these accumulation terms are nothing. There's no accumulation. So mathematically, if you like, that defines steady state. It's static, and so by definition, the velocity has to be zero. And so if we look at these expressions, if this goes to zero, then we just have the sum of velocities multiplied by mass flow rates equal the forces. So this term here drops out. We're just left with that. This is in the coordinate directions, remember. So it depends on the coordinate directions. I didn't draw those in, I guess. We always use the same coordinate system, which is right-handed. Probably doesn't matter in this course, right? X, Y, and Z, right hand. It simplifies to this, and because it's not moving, the velocity W out of the thing is the same velocity that you'd see as you're looking at it, which is just the same as the static velocity. Steady and moving was the vane. And so in this particular case, we did it in the x direction. What force R do you have to apply that keeps it in place? We start off with the same expression, steady. So by definition, no accumulation. Mass in equals mass out. This is important because from the question last time, if this sum of mass in minus mass out is equal to 0, if you multiply it by a single scalar value, then the term for both of these are 0, and this term just drops out. VCS isn't 0, but we don't need it anymore because all of the components that include that sum to 0. So we throw it away. And so that's the case here. So this VCS is not 0, but we can throw it away because of this reasoning that if sum of mass flow rates is equal to 0, multiplying that by a scalar is still 0. And so we're just solving for forces in one direction is equal to the velocities times the mass flow rates in. Mass flow rates are here, and mass flow rates out are here, but this has no velocity in the x direction, so it won't turn up in the equations. And so we need to be mindful of that. And finally, I guess, we did the case for unsteady and moving. So unsteady and moving means that the sum of mass in, mass out doesn't sum to 0 because it's accumulating stuff or losing stuff. As you can imagine for a gas cylinder, if you decapitate it, the mass is decreasing. So I guess in the terms of our conservation of mass equations, this is not changing. It's a steel container. but the density of the gas must be changing according to the ideal gas law. So if pressure is dropping, density is dropping, as you know. And so this is not zero. It's trying to move, so the control surface also is not zero velocity. And we need to keep this term, which is CS, which is the essence of the problem. And if we know what the mass flow rate out of here, which last time we did by using Bernoulli between upstream pressure and downstream velocity, those are the only terms that we have. If we know the pressure, we can calculate the velocity, v squared over 2g, square root it, and get the velocity. If we know this velocity is also w, right? It's coming out relative to the cylinder. It's its own kind of ecosystem that's contained as it moves anywhere. And so this is controlled by the external velocity. We need to include this. And as in all of these systems, as we'll use today actually, and as we did for the vane, the essence of this system is in this term here. These are vectoral quantities. So if W is going in this direction into our system, this is positive. And so we said there are two end-member conditions. The forces can only be zero if this right-hand side term is zero. We know that the mass is finite. Maybe it certainly isn't. The sum of the mass flow rates aren't zero. So the only way it can be zero is if these are equal and opposite to each other. So in other words, to be able to be equal and opposite, if I attach VCS to this, VCS has to be equal and opposite to this. So if you push in, if the flow is in this direction, that's not right. VCS, how is it? I'm having a brain burp here. The force is zero. The velocity W is in the Cartesian direction. I guess in this particular case, well, these have to be opposite to each other. So VCS, I guess, okay, so this is it. Don't draw it there, right? It was coming out of the decapitated cylinder, yeah. So it's coming out of here. So this is positive, so it was driving it in this direction. So I guess that is right. That's just the wrong place for me to put the arrow, right? This was W, which is positive. Brain burp there, so this has to be negative. Or it is in this orientation, which by definition is negative. And for the opposite case, where VCS is zero, where you're holding it in place, the force you have to apply is maximum. Okay. So that's what we did last time. So what we'll do now is make an easy step to use Reynolds transport equation again, but I'll draw on this. Okay, everyone okay with that, I guess? Okay, despite my lack of cogency. So, this is the sprinkler system, the one we saw on the lawn sprinkler. Water comes in along the length of it from an axis of rotation, I guess. I guess that's not, it's, in this particular case, it's really rotating around here, right? It comes out here, gets squirted out, and pushes so that the velocity at this thing would travel at would be in this direction. You could imagine that this is, the control surface is forced by the fluid going out of here to go in this direction. And so we could do something very complicated about, if you don't like dot products, you'll like cross products even less. But the cross product is just the lever arm that fluid has, which is r in this particular case, relative to the jet coming out and the location of action. So in the same way that we defined a Cartesian coordinate system as x, y, and z, right-handed, the rotational coordinate system is also a right-handed one, where this is the z-axis upwards, and the rotation direction is in the curl of the fingers on your right hand around it. Doesn't really matter for the things that we're going to do, but what we could do is we could take our system which we have here, our linear system, which was, if you remember, was sum of the forces is equal to mass flow rate times W plus VCS, sum of, with a bit of space, and we could multiply this by R on both sides, which is what you see here. So this is Reynolds' transport theorem written for rotational momentum. So moment of momentum is what that another way to call it. And it's just the product of this left-hand term with the radius and the right-hand term with the radius. A force times a lever arm is a torque. And so force times length is equal to a torque, the same as you apply on a wrench to be able to open stuff. If instead of the length being a length, if the length was for instance, a length over time, how far you're going in time, a velocity in other words, if this was a velocity, then this torque would be equal to, which would be equal to work, actually power. So I'm trying to kludge it to make it relatively straightforward. It follows directly from our idea of this vane. There's nothing special about it. We're taking the momentum equation, we're multiplying by a lever arm on both sides. This is the torque that's applied, and we can get that torque by knowing something about the velocities and where those velocities are relative to a center of rotation. And we're just using this exact formulation. All that's important now is that instead of being an x, y, and z coordinate system, you can imagine this coordinate system, I suppose, being attached to the end of a rotating arm. This is always tangential to the arc that this carves. Will only work in the horizontal plane. The right-hand rule that I said is up through my head, and so this is the vane that's going around us. So I don't know. Don't know if you get that on the recorded version, so being in person is good. So this is it. So if I haven't done a good job, this in microcosm is what we're dealing with for the sprinkler, and those are the expressions we need. The top expression I can write more simply as sum of W plus VCS mass flow rate times R equals sum of flow rate, sum of force times radius. The force has to be in the tangential direction, which we'll call phi. This rotation that we go through, I guess, is an angle theta, and this is the angular velocity. Omega equals angular velocity, which is equal to, which is in radians per second. And you have the different conversions here. So, and we'll do an example with this. So this is the vane. Water comes in through along the radius and goes out at a right angle. This component isn't going to have any component in this direction because it's coming into it. It rotates through some angle theta. 2 pi will be one full rotation. The rate at which it goes through that angle is called lowercase omega. and we can write it in terms of a force times a lever arm. This is just the lever arm multiplied by a lever arm and the velocity. This is the momentum balance equation. We call this a torque, the force times the lever arm, and it's given by this. We know that the mass flow rate is going to be the velocity of water across this boundary out of the system multiplied by its area and density. That's the amount of the mass that's coming out per unit time. And if we multiply that mass, which is always going to be, this is always going to be positive outwards. Out of the system. It's coming out of the sprinkler, so it's positive, plus VE. Thanks for asking that question 6 weeks ago. Otherwise, you'd still be wondering. And these are the velocities tangential to this rotation. So this is the tangent of this line here. So it's the velocity angled in this direction, W. So this would be W if it was an angle coming out here. Then we would want the component along here. So if this was W, then this other length here, didn't want to do that, doesn't catch very quickly. If this was W, then this would be aligned in the direction of rotation. So this would be W, this would be theta, and this would be W cosine theta. We'll do an example, so it's not all just equations. And so the other things you need to know are that 2 pi radians a second for the angular velocity is 1 revolution per second. The angular velocity as a length per unit time is the radius multiplied the angular velocity in radians, just as convention. And the torque times the angular velocity is equal to the power. Let's not call it that. Watts, joules per second, or watts. So we're getting to somewhere where we could use this, right? We're going to squirt water out. We have linear momentum of the flow to the head of this thing. This is just linear momentum of the water. We turn it 90 degrees, and we turn it into some useful energy by turning it into rotational energy. And of course, that's useful because you could have a generator attached to this and create power from it. And so you have that going. So that's it. So maybe it's worthwhile doing an example. This is the example, again, in microcosm. Let's look at the example. It's in the notes. And by the way, there are some examples for linear momentum as well. We didn't really do any this year, but if you look back in the previous years, you can find them. So cross products means a lever arm. You can do it in arbitrary. So if you have something spinning relative to the Cartesian system, you can use the cross product to get that. We don't need to spend time doing that. It's the determinant of a tensor, blah-de-blah, doesn't matter. But we just need to know this. You got it? Yeah, fine. This is the problem. So a bit more sophisticated than the sprinkler we talked about. So we have water coming up into this, comes in at 5 liters a second, goes out through 3 nozzles at the edge, and those nozzles are directed so that they could be perpendicular to the circle, the tangent to the locus of the points on the boundary, which is this circle. I guess it doesn't have to be a complete, these could just be individual sprinkler heads, but I think the drawing here is that it's a disc that just has some holes coming out of it. We're interested in the velocity parallel to the thing. And so if it comes out at an angle, we have this velocity, but we need to know the component which is normal to this boundary, normal to the radius of rotation. And so what's it asking? Water comes out at 5 liters a second. It comes up through here. It goes out. So it goes through 90 degrees. So we know that because of that, we really only have to look at the behavior. We don't care about this stuff coming in, but we know that the stuff coming out also has to be coming out at 5 liters a second. It's 5 liters a second, but it's on 3 nozzles. So a third of it will be coming out of each one. And so we do need the velocity coming out, and we also need the mass flow rate. But the velocity will be per nozzle. So we'll need to deal with that. We know that the area of the exits on the nozzles is 18 millimeters squared. Square root of 18 is, so 4 millimeters is half a centimeter by half a centimeter. So 2/10 of an inch square. Two end member conditions. What torque do we have to apply to hold it static? So it's a torque now because it's a force at the outer reaches of this multiplied by the lever arm. So the torque you have to apply in holding this static. And if you leave it to spin, how fast it will spin when the inclination of the thing relative to the jets are 30 degrees, 0 degrees, 30 degrees, and 60 degrees. Okay. So, what do we need? We're going to use this expression. The expression we use is going to be, as we've written it out, force times radius is equal to sum of radius W plus VCS times mass flow rate. This W has to be in the parallel to this. This is the angular velocity, the velocity which would be meters a second, but directed parallel to the outer radius of this arc. And so if we look at that, we see this. These terms translate here. This term here is torque. Not writing that very well. Q-U-E, not toke. Torque is force times the radius, and that's what we want to calculate. That's the torque we have to apply to hold it static. Mass flow rate is going to be 5 times 10 to the minus 3, 1,000 liters in a cubic meter. Equals m dot, which is this. The radius is going to be half a meter. And the velocity out is going to be equals Q over area, which is 5, it's probably written down there, times 10 to the minus 3, divided by 3, because there's 3 of them, divided by the area, and that's must be 18 millimeters squared, which will be 18 times 10 to the minus 6, right? It's 8, yeah, I think. And so you have that exactly here. Velocity out, which goes up here, is equal to the flow rate times divided by the area. There are 3 nozzles, so per nozzle, that is the velocity. If you don't divide by 3, you don't get the right magnitude. Mass flow rate is just the density multiplied by the volumetric flow rate. So actually, I was wrong. You have to multiply by that, of course. And if you include the component that is in the direction that's tangential to the rotation, to the arc, then you get cosine theta. So you make those substitutions, and you get a torque that you have to apply. So if you go through the units, I'm always loath to do this after I screwed up last time, but what are the units of this? The units are kilograms per meter cubed, meter cubed per second, meters, cosine doesn't have anything, and areas are meters squared. So that would be equal to flow rate squared. Thank you very much. So that is another meter cubed over second. Thank you. That might save my bacon. So what else do we get? We keep kilograms. We end up with, this is meters 4 over meters squared. And this is seconds squared and kilograms. So kilogram, yeah, okay, and I can write that out. So kilogram meter per second squared. So kilogram, these are meters squared. So a kilogram meter per second squared is a Newton, and it's multiplied by a meter, and that's equal to, as you know, a joule, which is the torque, right? A Newton meter. And that's why if we look at torque per unit time, it ends up being power, right? Joules per seconds is watts. Did it work out? Did it right? Thank you for the velocity, the flow rate squared. So the next question is, what happens if you let it run? What are the velocities it runs at? Well, intuitively, they don't have 90 degrees on here. Intuitively, if it's squirting out normal to the boundary, you'd think it wouldn't be going anywhere, right? It's all in equilibrium. So by the same token, if it's going tangential to this, you'd think that it'd be going fastest if it was directed directly along this line. If it was coming at various angles, they'd be progressively slower until it got to the full angle. So let's write the equations again. So going back to our expression, this is the expression we have. Torque is equal to radius velocities times mass flow rates. Torque is equal to radius velocities mass flow rates. Mass flow rates is positive outwards, which we got before, which is going to be which is equal to volumetric flow rate times density. Which we can get. So we can get this. The radius is the same as it was before. It's 0.5 of a meter. And the only interesting thing are the components to go in here. It's written slightly differently. We would write it as W theta cosine theta plus VCS would be how we would write it. We've written it before. Right? So this is kind of how we write it, just from our conversion. But we use this to represent these are vectoral quantities. They have direction as well as magnitude. And so we have to be, it's the same as the gas cylinder, which I nearly screwed up but recovered from. And that if you have a jet going out of the gas cylinder, it moves in the opposite direction. And so they, in this example, have just defined their coordinate system as this is W, but this is positive U, and so they're subtracting it from it. And so they've just defined it in that way. So we would write it this way and be mindful of the fact that these are vectors. They've written it in their own coordinate system in this example, where this is positive. And so this is the expression you get, and then you can solve it for those various conditions. So we know this expression. And so if we choose a magnitude of tangential to the arc that it goes through, then theta is 0. You throw numbers into here. We have a density. We have a volumetric flow rate. This is 5 liters a second. This is 1,000 kilograms per cubic meter. This is a half meter. This is whatever the volumetric flow rate is, 5 liters a second, 5 times 10 to the minus 3 meters cubed per second, 18 millimeters squared. Cosine 0 for this, the first one, is actually 1. And this is the radius times the angular velocity. So u is just equal to the radius times the angular velocity. So this would be 0.5 meters. And this would be in radians a second. And we said that 2 pi equals 1 RPM. RPS, I guess. Revolution per second, right? Shorthand. So you have it all here with the conversions. And if you hold it static, you end up with this being the torque you have to apply, 231 Newton meters, joules. If you allow it to rotate, so if this is 0, which is the case for that, this will only be 0. This is a finite term. It'll only be 0 if these match each other. So if these match each other, you can find out where that happens, and it's rotating at 185 radians a second. So that's the case where you have, it does, I wanted a circle. So that's the case where it's squirting out, bless you. So that's the case. So you get 231 Newton meters, and if you let it go, you get a rotation. If you change it so that you now do this at 30 degrees, which was one of the numbers. Interesting that the little icon for this is a cross hairs rather than anything else. So at 30 degrees, what do you expect to happen? Torque less or more, and velocity less or more. 90 degrees is going to be what? 0. Torque 200 instead of 231. Velocity 160 instead of 185. 60 degrees, the same trend. Shaft torque instead of 285 and 200, and it's now 116. And the velocity, instead of being 185 rads, going to 160, going to 92.5. And you know, the coup de grace in this is if phi goes to 90, then T zero, right? You know that. So that's it. So kinds of machines that we need, we want to change linear momentum into rotational momentum because machines use that quite well. It's the idea of a water wheel that powers a turbine or grinds corn or corn for that matter. And the summary behavior, I guess I'll go back to that slide right at the beginning, which we rushed through. The summary behavior for this is right here. I've told you already rotational momentum isn't on the midterm, so you don't need to shut this out. But the expression is this. It's different from the one we just looked at because these are in the same directions. And so if you have them defined differently, you have the subtraction. This is always the out of the system velocity component that's tangential to the arc of rotation. This is the torque, which is a force times the radius arm. Yeah, the radius is on here. Mass flow rate sign convention is always positive out of the system. This is always positive in a given direction. Ostensibly, the right-hand thumb rule doesn't really matter. It just means that the velocity of flow out of the system and the velocity of the control surface, if the torque is 0, they have to be equal and opposite to each other to be able to make this left-hand side 0. And so the torque per nozzle was this. The mass flow rate is Q over 3 times the density. This isn't an angle relative to the boundary because it's just mass in or mass out. It doesn't care the direction. It's just across the control surface. But this is an angle. And if you have 3 nozzles, then the torque is just 3 times the torque for 1, which is 3 times this. The 3 and the 3 cancel out, and you end up with this. And the important end member conditions are this. If you let it run freely, it goes at the max speed. Makes perfect sense. Just like shooting a jet onto the vane, it will run away from the jet exactly at the speed of the jet as it reaches it. And this is no different. If you want the velocity to be 0, that's the maximum resistance you have. And then I guess the other component in this was what we talked about, was that we drew these 2 diagrams, one for force and one for velocity. So this is velocity of the control surface relative to the velocity of the control surface. This would now be the torque, which is equal to the force times radius. And so at 0 velocity, the torque is a maximum. VCS versus VCS is just linear. And so if you look at the product of those two, which is the whole reason for doing this, if we look at VCS times torque, then the relationship we have is this. Good. Fantastic. If you're holding it static and the torque is maximum, you're not doing any work because it's not moving. If you're allowing it to spin freely, there's no force being applied to it, so it's not doing any work either. So only somewhere in the middle will the power, max power. So, theory of machines and why we're interested in changing linear momentum for a jet into rotational momentum, because you can use it to generate power quite simply. Okay. That's it. All right. Great. It did fill out, so people did come. It was very sparse earlier on, so great to have you. Any questions before we get going?